Okay, so we're going to now talk about something that's again disintegrating. It's called a three-piece explosion. So you have a 10-gram projectile traveling east at 2 meters per second when it suddenly disintegrates into three pieces. A 3-gram fragment is shot due west at 10 meters per second, while another 3-gram fragment travels 40 degrees north of east at 12 meters per second. And the question is, what are the speed and direction of the third fragment? Well, first of all, I hope you can see that the third fragment will have a mass of 4 grams, because the first two fragments are 3 and 3, that's a 6. The total mass is 10, and so that fragment will be at 3 grams. I'm sorry, 4 grams. So let's draw the situation. Solution. So before anything happens, we had 10 grams going east at a speed of 2 meters per second. This is before. After, well, what happens after is it's broke into three pieces. The first piece is 3 grams. The first fragment is 3 grams and travels due west, so west, this way, at 10 meters per second. 10 meters per second. The other one, or another one, is also 3 grams and travels 40 degrees north of east. So here is another 3 grams. And it travels at 40 degrees north of east at 12 meters per second. And then the third one would be 4 grams. Here it is. The question is, in what direction will it travel? First, we only have momentum in the x direction, so we better have only momentum in the x direction. This one has momentum in the negative x direction. This one has some momentum in the positive y direction. So this one better have some momentum in the negative y direction to cancel that. That's what my intuition tells me. And then this one is moving to the left. This one has some momentum to the right, but we have to make up for the total momentum to the right. So this one possibly needs to have some momentum this way. And so probably the direction of this will be like that, I'm guessing. Let's do it for me. So we will write that the momentum before collision, before the explosion, will be the momentum before, total momentum before, it's only in the x direction. It's 10 grams times 2, and that's 10 grams is 0.01 kilograms times 2 I hat, and so that is 0.02 kilogram meters per second in the I hat direction. That's the total momentum before. Let's look at the total momentum after. P final. P final. Okay, we'll start with this one. This one has only momentum in the x direction and it's negative. And how much is it? Well, it'll be mass times this, so it's 0.003 grams times 10. So 0.003 kilograms, because you divide grams by 1,000, times 10 meters per second. And then it's in the I hat direction. The fact that it's negative is there. This one will have two components. One of them is the mass times the x component of velocity, which is 12 cosine of 40 degrees. And this way, 12 times the sine of 40 degrees. That's the y component of velocity. So for the other one would be plus, the mass is also 0.003 times 12 cosine of 40 degrees. That's the x component of velocity, so that's I hat. And then plus 0.003 times the y component of velocity, which is 12 sine of 40 degrees, and that's j hat. And then plus the momentum of this fragment, which is the third fragment. I'm going to call it P3. P3 will be P3x I hat plus P3 y, and it's j hat. I don't know what they are, so I'm just going to keep them in symbols. So it will be plus P3, the third fragment, I hat plus the third fragment in the y direction, j hat. So let's add these and see what happens. So we get P final will be, let's add them. We need probably a calculator here. Let me get my calculator just to make life easier. Let's add the I hats together. You get negative 0.003 times 10 plus 0.003 times 12 times cosine of 40 plus 0.003 times 12 times the cosine of 40. So that gives me, I'm going to write that down in the x direction. That will give me negative 0.00242 I hat. That's from fragments 1 and 2, plus P3x I hat. So let me put it this way, plus P3x, the whole thing, I hat. And then plus, now the y direction, it will be, this doesn't have any y direction, only this one has a y, and this one could possibly have a y. So this plus this. So we will do 0.003 times 12 times the sine of 40 degrees. And then that gives me 0.02314 plus P3y j hat. So that gives 0.02314 plus P3y. That's in the y direction. That's the momentum at the end. And now we're going to set the momentum at the end equal to the momentum at the beginning and see what it gives us. So you get P initial equals to P final. P initial is just 0.02 I hat. So we get 0.02 I hat, that's P initial. And it has to equal to the P final, which is negative 0.00242 plus P3x I hat plus 0.02314 plus P3y j hat. They have to be equal. So the I hat has to equal to the I hat, and the j hat has to equal to the j hat. The j hat part here for P initial is 0, so this part has to be 0. So let's worry about the I hat part first. We will match this with this. They have to be equal. So we get 0.02 equals to negative 0.00242 P3x plus P3x plus P3x. And so we get P3x component will be the 0.02 plus, actually. When you take it to the other side, it becomes plus 0.02 plus 0.00242. We get 0.02242. That's the momentum P3x. But what is P3? What's the momentum for P3? Well, it's the mass times the x component of velocity. So it will be this mass times the x component of the velocity. And so we get, right, this is just the mass of the third fragment times the x component of the velocity for the third fragment. So we get the velocity for the third fragment, the x component, will be 0.02242 over the mass of the third fragment, which is 4 grams or 0.004. And let's see what we get over 0.004. We get 5.6, about 5.61 meters per second. That's the x component velocity. And now we're going to match this with the j component here, that's 0. So that means this and this, they have to add up to 0. And also, so we say also, we get 0.02314 plus P3y equals to 0. So P3y will be negative 0.02314. And so Vy will be, because P3y is the mass of the third fragment times the velocity of the third fragment in the y direction. So we'll just divide by the mass and we get, divide by 0.004. So 0.02314 over 0.004, that gives negative 5.79. Negative 5.79 meters per second. That's that. I think they said the speed and then what is the direction. So for the speed, will be Vx squared plus Vy squared. So you square this one, and you square this one, and you get the direction. I'm sorry, you get the magnitude. Okay, I got 8.06, about 8.06 meters per second. That's the speed. The direction, well, it's 5.61 units this way and 5.79 units this way. So this is negative 5.79 and this one is positive 5.61. And so the velocity is in this direction. And we would like this angle. So it will be slightly more than 45 degrees because the y wins. But it's below. So we get theta then will be tangent inverse. If you like, you can just plug in the y and the x. Would be Vy over Vx. And it will give you negative what? It would be below the x-axis. So it would be tangent inverse of 5.79 over 5.61. I always just put the positives and then if there is a minus sign, I put it myself. I got 45.9 degrees. And I know it's negative because it's below the x-axis. And let me just double check my answer, just to be sure. Everything looks good. Okay. And now I would like to talk about a couple more things. The last topic will be the rocket propulsion, and we're going to look at an example where the mass is changing. So we have something that has an initial mass, and as it goes, it loses fuel, it fires fuel, and so the mass changes appreciably, and therefore we have to consider the mass changes. Okay, and so let's start with a sketch and then go on. So here it is. So imagine you have a rocket and it's just horizontal. It has an initial, let's say, mass m, right? And it's moving at a speed v, right? It's moving at a speed v. It starts from rest, and at some moment it has a speed v, and it's moving in that direction. Okay, let me get my pen. So a little bit later, it will eject fuel. After a time delta t, it will eject fuel backward, and it will gain velocity. So the velocity after a moment will be v plus an amount dv, plus dv. But it will eject fuel this way, which has a mass dm, and it will be moving this way at a speed u relative to the rocket. So let's say the rocket is moving 100 meters per second, it will eject fuel, let's say, at 10 meters per second. So the speed of the fuel relative to the ground will be 100 minus 10, which is 90 meters per second. Because at the end, we want the speed of the fuel relative to the ground, to some observer who is sitting here. Right? The rocket will always, let's say, imagine like you're in a car and you constantly keep throwing balls at 5 meters per second. Regardless of how fast the car is moving, you're still throwing balls at 5 meters per second. But relative to the ground, they have different speed. So we will worry about that in a moment. The mass of the rocket afterwards will be the mass of the rocket now plus dm, with the understanding that dm here has a negative value. It's negative. It has some negative value. We could use minus sign, but then everything changes. I'm just sticking to the notation of the book. So please understand that dm here, that is the mass that you lost, so it's some negative quantity. So it's, let's say, 5 kilograms plus negative 1 gram, let's say. Negative 1 gram or something like that. Okay. So this is u, the speed of the fuel that's ejected relative to the rocket. Okay. So we would like to use conservation of momentum. So we would say the momentum at the beginning should equal to the momentum at the end. Beginning meaning at this instant, and then the momentum a little bit later. The momentum at the beginning is just mv, mass times velocity. The momentum at the end, you have the rocket itself, which has this momentum. It's the mass later times the speed later. So it would be the mass plus dm times the speed later, which is v plus dv. Okay? And then plus the momentum of this thing here. And what is that momentum? It will be u times dm, but that's relative to the rocket. We would like it relative to the ground. Okay? So, first of all, momentum as usual is mass times velocity. The velocity of this dm relative to the ground, again, imagine if the rocket is going at 100 meters per second and ejects fuel at 10 meters per second this way. Relative to you, what's the speed of the fuel? Well, it will be 90, because, like, again, let's say I'm going this way at 100 miles an hour, and I throw an apple to the left. Relative to me, it is at 10 miles an hour, but relative to you, it has 10 miles per hour this way, but it carries my speed, the speed of the car, so that would be 90 miles per hour. If you are confused, review the relative motion. Okay? So it will be this speed minus u. So it will be the speed at which it was, from which the rocket was moving was v minus u. If you like, it's v plus dv, but at the end the dv will drop because it's tiny. So it'll be v minus u. Now, the mass, remember the mass, we always put the magnitude of the mass times the speed, or times the velocity. What's the magnitude of the mass? This dm is negative. So I have to put a minus sign since the dm itself is negative. So I put a minus sign. And now we're going to open this. So we have mv, we're going to FOIL this. I have mv, and then mdv, and then plus dm times v, so that's v times dm, and then dm times dv, and then negative dm times v, or v times dm, and then minus times minus is plus, and then dm times u, or u times dm. So let's cancel a few things. So you get mv cancels mv, so the left hand side you have 0. mdv, or vdm and negative vdm, they cancel each other. So here I have mdv. Now dm times dv, dm is a tiny amount, is an infinitesimal amount, times another infinitesimal amount when you, because we're going to integrate and we're going to take the limit as dv goes to 0 and dm goes to 0. Both are going to 0, so their product is vanishingly small. So in the limit, it will be 0 regardless, even when you integrate infinitely amount of them. So this is basically 0, 0, because it's two infinitesimal amounts times each other. And then plus this last term here, u dm. I'm going to move this to the left side and then set them equal. So I have m dv equals to negative u dm. If you move to this to the other side, it's really this one that's negative and this one is positive. But I would just multiply both sides by negative 1. So this becomes the plus and that becomes the minus. Now I'm going to divide both sides by m. So I have dv is equal to negative negative u over m dm. dv over dt is the force. So let's see what the force is. I'm sorry, dv over dt is the acceleration. The acceleration, I'm going to come back to this in a moment, but for now, let me just use it. So I'm going to divide both sides by dt. So this dt will be, the acceleration will be negative u over m, and then dm times dt. And actually, I shouldn't have, let's multiply both sides by m again. So I have ma will be negative u dm dt. dm dt. This quantity of dm dt, the magnitude of it, is called r. And I forget what the term was for it. Okay, yeah, it just stands for the rate at which the fuel is burned. I don't see a name for it. So dm dt is just how quickly you're burning the fuel. And this rate will be usually typically constant. dm dt will be some constant number. It's usually called r here. And so you have ma will be negative u times r. Or actually the absolute value of this dm dt, even with the minus sign. So let me just leave it like that. And then, so ma is the force. So this force here, u times r, is called the thrust. This is the thrust. That's the thrust. It's just called the thrust. All right. So let's come back to this. We would like to figure out what v is later. Let's just use this one here. So I'm going to, let's say the rocket started at 0, and I want to know what the speed is at later times. So I will integrate both sides. So I have dv equals to here negative u, the integral of dm over m. Okay. V goes from, if it started initially at 0, so from 0 to v. If you like, you can put a prime here. And the mass of the rocket will go from where to where? Well, it will go from the initial mass of the rocket, which is the mass of the rocket plus the mass of the fuel, and then until you burn all the fuel. So you remain with just the rocket itself, mr. So let's integrate this. So the integral of this is just v minus 0, which is v. For this one, dm over m, the integral of 1 over x is the natural log. So it will be negative u times the natural log of m evaluated between mr plus the fuel, mass of the fuel, to m of the rocket. And so v will be negative u. And remember, when the difference of natural logs is the ratio of their difference, the ratio of their arguments. So you get natural log of mr over mr plus mf. I'm using this, if you remember, ln of x minus ln of y will equal to ln of x over y. And this minus sign, I don't like it, so so it will go here, becomes the exponent, and something to the minus 1 is just the reciprocal. So this is just v will equal to u times ln of the mass of the rocket plus the mass of the fuel over the mass of the rocket, like so. Okay. And that would be your final velocity. The velocity starts at 0 and then increases to some value. Okay. I want to do a problem on this, but let's just do it in the next video because I'm running out of time.